So, all right, here we go. Miss Mendel, what do you think?
Well, you said one of them is going to be the nickel, but you didn't say the other one.
Exactly, that's it.
That's it.
That's it. Yeah. So you're right.
This is a math problem. This is
Well,
an English problem.
yeah, math and English are very similar. They're both based on syntax. Try diagramming sentences. That's pretty dumb. All right, here we go. Here we go. Okay, so for today, close them up. Close them up. I'm gonna go through. Probably shouldn't. How long? We'll see. I want to get through some things though, so you got stuff to work on tomorrow. We're going to take a look at some more stuff with graphs. We're going to look at some characteristics of graphs. Real quick, just a little review. What am I going to do in a problem like this? So we're dealing with functions, and a natural outgrowth of functions is the graph of functions, graphs of functions. We're going to do a lot more with this in the future, but we just want to make sure we're clear with all the concepts. So if I have volume of a sphere, and I know that the radius is given by, the radius is 5, 6x, what would I have to do if I wanted to write volume as a function of x? Substitute. Right? Everybody see that? That's all I'm doing. I'm substituting 5, 6x goes in for r, right? So I've got that quantity, and then I would just simplify using properties of x, no big deal, right? Okay? What about something like this guy? It has a length of x and a width of that. What's the perimeter of the rectangle going to be given by? Think about that one for a second. Now we're looking at part 1 here. So what's our formula for perimeter of a rectangle? Right? Okay, so if the length is x, I'm just going to get 2x plus, what's the width? Well, it's that whole thing, right? So that's my expression. It's not simplified, but I could just distribute the 2 and add like terms and simplify it, right? Okay. So then what about part 2? When the length is 6, the perimeter would be what? What would I have to do?
Input the 6.
Input the 6 for the x, right? No big deal. Okay. Now, what if, I didn't ask this question, but this is a little tougher. What if we said that when the width is 6, what's the perimeter? What would I have to do? Okay, good. I'd have to set the whole perimeter expression equal to 6 and do what? Solve it. I have to solve for x. I might get multiple solutions, so there might be multiple ways that could happen, right? Theoretically, okay? Geometrically, it may not pan out that way, but theoretically it might, okay? Anyway, so, all right, so we want to talk about, one other thing too, so average rate of change. So if we're going to look at the interval from -8 to +4, everybody quickly, why don't you just get out your note paper or your notebook and just scratch that out. Tell me what's going to be the average rate of change function. Negative 1/3, that seems about right, let's check. So at x equals negative 8, what's the value of the function there? It's like 4. So we're at the point negative 8, 4. At x equals 4, the value looks like 0. And so, you know, we can do this in terms of, we can think of this in terms of kind of an average rate of change formula if you wanted, right? What did we say an average rate of change is always equal to? Okay, so it's the slope of the secant line. It's the slope of the line connecting those 2 points on the graph. That's one way to do it. We can do it graphically, which is probably, you know, what this is getting at, 'cause it's giving us a graph. And if I were to draw a slope triangle here, the rise is negative 4, while the run is 12. And so we get negative 4 over 12 is negative 1/3. What's our definition, just our mathematical definition of an average rate of change of a function? Say it again? Change in y over change in x, right? So the average rate of change is delta y over delta x. Well, in terms of a function, what is delta y? Sure, those sound like coordinates though, right? If we're talking about a function, that's just the change in the output, right? So it's always going to be the final output minus the initial output. Does that make sense? Okay. So it's going to be like, in this case, it would be f of 4, f of 4 minus f of negative 8 over, right? That's the top, change in y. The output of the function at 4 minus the output at negative 8 divided by what? What's the change in x?
That is not h x.
Say it again. No, that's not. That's not the change in x. Let me write it down here. So it's going to equal f of the final value, right? F of 4. Whatever, and this function up here, you know, we don't know what this is, but we're just going to call it f of x if we're thinking of it like a function, right? So we've got f of 4 minus f of negative 8. That's the same thing as delta y, isn't it? Right? Because over delta x, what's delta x?
4 minus negative 8.
Okay? So the change in the output values over the change in the input values, right? Final minus initial.
Why is that?
Why?
It's obviously 4 minus 0.
Well, no, you're right, but it's f of 4. What is f of 4? Oh, sorry.
That's 4 minus f of 0.
No. Mm-mm. Am I doing something really dumb here?
Yes, it is.
Yes.
The y.
Yeah, but what is, so you guys are claiming it should be 4 minus 0, right? That's not right. No.
If you don't have the
No. What is f of 4? What is f of 4? No, f of 4 is 0, right? What is f of negative 8? 4. That's giving us the rate of change, right? But this in general, if we're writing it as a function, the point I'm trying to make here is that this is how we look at an average rate of change as a function. It's always going to be, if we say that x, let's call it x sub 0 is the initial input, and let's just say x sub f is the final input. Whatever that might be, time, it might be, who knows what we're measuring with our function. Could be time in years, it could be the number of products sold, who knows what we're talking about. Some kind of an input that we're in our function, right? If that's true, then the average rate of change is always going to equal the value of the function at the final input minus the value of the function at the initial input divided by the final input value minus the initial input value, right? So we're saying f of x, f of 4, doesn't say 4. That means the output value of the function when I input a 4.
So that's actually 0.
So that's, right, now if we evaluate the function, right? And these words are important. If we evaluate the function, if we're going to figure out what the value of the function is at 4, that works out to be 0 minus negative 8, minus 4, sorry, it was 4, wasn't it? Right? This is 0, that's 4, divided by 4 minus negative 8 is 12, right? There's our negative 1/3. Okay. But the idea being that we don't always, now we're kind of focusing on graphs here, right? We're looking at graphs. In graphs, it's really easy for us to think about this in terms of x's and y's because it's on the xy plane. But a lot of times, when we're talking about an average rate of change for a function, the function's representing something completely different. But it's always, an average rate of change always means the same thing. It's the final output minus the initial output over the final input minus the initial input, every time, okay? Questions? Okay. All right. Next issue. So this is something a little bit new. So now we're going to start to just look at a really simple introduction to sort of the topology of functions. We want to look at how do we describe the landscape of a function here. It's a pretty boring landscape. It's two-dimensional. But this is what we do in calculus a lot. In calculus, we do a lot of what we might call real analysis. So, or it could be complex. Might use imaginary numbers in college and make a complex analysis. But we want to look at a function and we want to be able to describe the interesting parts of the function. Because functions model real things. Like there were companies who, when I graduated from college, there were companies who were essentially hiring people without an interview. If you had gone through the program in analytic program, if you had gone through math, you were a math major, you were a physics major, or you were an analytical chemistry major, they were going to give you a job without even interviewing you to become a quantitative economist, and then you'd have to move to Wall Street. But people made just tons of money doing this stuff. What were they doing? Essentially this. Essentially they were studying economic trends, looking at functions that would model economic trends, so that these companies could have a slight advantage over their competitors in trying to figure out which investments to make, right? Things like that. And so functions aren't just graphs on the XY plane. Functions, a lot of times these graphs model real things, right? And so we want to start at the beginning, but when I see you guys in calculus, what we'll do is we'll spend a lot of time talking about how can we be much more sophisticated in our treatment of these functions. How can we find all the interesting places? For a difficult graph, how could we find the places where we're going to get a local maximum or a local minimum? Or how could we find the places, the inflection points, where the concavity of the graph shifts from positive to negative? And these are all words you don't know yet, but they're coming down the line eventually. And when we get to calculus, these will become very familiar to you. We're going to start right now with pretty simple graphs, and we're just going to look at some of the features of a graph. Like some things we might want to consider is where is a graph positive valued or negative valued? It's a pretty simple idea. Now, what do you think that means? If we want to find the intervals where this function is positive valued, suggestions. Where are we going to start our look? Where do you think a function would be positive valued? Where it's above the x-axis, right? Because the function corresponds to, y is, or f of x is just a fancy name for y, right? The output of the function is just the y coordinate, right? We're talking about the value of a function. We're talking about, is it above the x-axis or below the x-axis? So on this graph, we want to write these intervals, and let's write them in two ways. Let's write them using inequalities and interval notation. And on the assignments, I'll ask you typically for one or the other on a problem, not both at the same time, but you got to know how to do both. So first of all, maybe let's graph those intervals on the x-axis. And think about this in terms of that smooshing down onto the axis we talked about the other day. So if we take just the part of the graph that's above the x-axis, and I smush it down onto the x-axis, what marks would it make on the x-axis? So what are the parts that are positive value? Okay, so this part up here, everybody agree?
Yeah.
That's a part that's positive valued. And then right here? Okay. So if I push that onto the x-axis, what would the graph look like? The graph of that inequality. Okay, so I got a line from 6 to 8. Good. Okay, I need some more detail there, though. What about the endpoints? You see the problem there? We gotta make a decision. What are the two possibilities for the endpoints? Open or closed? Now think about this for a second. Which ones it have to be? I think closed. Let's take a vote. We're a democratic society here. Let's take a vote. How many people say, give me a closed? Give me a vote. Okay? Open. Give me a vote.
Yeah.
Right here? You want to buck the system?
No.
You sure? Because you'd be right.
I'll bump the system now.
I don't,
So-
can't explain it.
It has to be open. Why?
Because
Because we're asking for the places where the function is positive valued, right? What are the coordinates? Let's take this point right here, for example. What are the coordinates of that point? 8, 0. Okay, is 0 positive? No, it must be negative. No, it's neither, right? 0 is the boundary between positive numbers and negative numbers, but it is neither, right? So if we want to know where the function is positive valued, it's only positive valued on that open interval. We're not including the endpoints. So given that, what do you think we're going to have over here? Okay, good. Open, endpoint, and then off to the left indefinite, right? So how would we say that with inequalities? This part would be x is less than 3, or, right, x is what? I guess I need to, or x is what? Greater than 6 and less than 8. Okay. What if we wanted to write this using interval notation instead? So what's this part going to look like? Negative infinity. Open. And then we'll just go comma. Okay, comma is going to separate intervals. That's one way that we do it in math. We do it several ways, but that's the way we're going to do it. Okay? Okay, no big deal, right? Okay, what about, whoops. Okay, let's ask a different question about this. Okay, so this time I don't want to know where it's positive valued. I want to know, and by the way, in the last one, where it's negative valued would have been almost the same question, right? It just would have been where it's below the x-axis, okay? This time, though, I want to know where it is increasing. That's an important math word. What does increasing do, at least in terms of math? Positive slope. Ah, very good, right? Positive slope. So if we think about this, and this might sound a little dorky, but we do this a lot in calculus. We talk about an ant walking on a function. So if an ant's walking on a function, if the ant's walking in a positive direction from left to right on the graph, if the function is increasing, positive slope, what's that mean about the ant's progress along the graph from left to right? What's he doing? Going uphill, right? He's rising, going uphill. So, how could we maybe make that a little more mathematical? Any suggestions? And that seems pretty good. But in math, we'd consider that an informal argument, to say that the slope is positive. We want to be able to say something, if we want to be really particular about this and make a more formal argument in math. We're not going to do this a lot, but I want you to get used to this idea. We want to say something about, well, how can we describe this without invoking all these other words, like positive slope? There's a whole other thing we got to talk about, that we got to define that. I want to add something to that?
I was gonna go with which one of the
Okay, I mean, we're on the right track with that. Seth? Okay, so now we're getting somewhere. So what if we said something like, we're gonna pick two values of x. Let's just pick some numbers. Let's say if something like, if b is greater than a. So we got some real numbers, a and b, and if b is greater than a, if the function is increasing, what would we have to say about the outputs at these values? So if the function is increasing, what would have to be true about the relationship between f of b and f of a? Say it again. Well, okay, so b is like the final value, right? Because if we've got two values, like this might represent, what are two examples? Like 7 and 3, right? 7's greater than 3. We're just picking, but we're not going to specify. We're saying just any real numbers such that b is greater than a. Then what has to be true? I'll just make an arrow here. We can add some more language to this, but I don't want to write that much, so I'll just go to the next slide and we'll see the formal language. But I want you to get the concept down. So f of b would have to be greater than f of a, wouldn't it? Right? If the function's increasing, for a value of b that's greater than a, that means to the right of a, doesn't it? On a graph, the y value would have to be greater than at b than at a, so it'd have to be moving uphill. Everybody see that? Now, if the function were decreasing, that would flip the inequality around, right? So when b is greater than a, f of b would have to be less than f of a. So that's what we call a formal argument in math that we're describing. That's bulletproof. If that's true, there's no way to dispute it if the function is increasing, right? We can see it graphically very easy though, right? Where does this function, give me an interval, somebody different here, on which this function is increasing. And you might have to estimate a little bit. They're supposed to be convenient. They don't always, it doesn't look like they always work out to be exactly right.
4%.
So about 4 to 7, yeah. When I program these, the questions where it asks for increasing and decreasing, I program the graph so it works out to be, this one wasn't really built for that. So just kind of pretend it is though. So yeah, pretend this point is right there, and pretend this point is right there. So it looks like from about 4 to 7. Everybody agree that's the interval where it's increasing? Okay, but when I draw that on the x-axis, there's 4 to 7. So I'm going to smush this onto the x-axis. What about the endpoints? Are they going to be open or closed? Let's vote again. What do we say? Open, raise your hand. Closed, raise your hand. We'll give you another chance. Open, raise your hand.
Oh, wait.
Okay. Yeah, I know you're doing reverse psychology here. You probably think I'm trying to trick you, right? Closed, raise your hand.
I think.
Okay.
Somebody's sweet.
Drum roll. The answer is open. Open. Now let's think about why that is. Because if the ant's walking along this function, when he gets to the bottom of that valley, is he walking uphill or downhill? Neither, right? It's between the two. Agreed? Does that make sense? Yeah. At that point, the ant he's on the boundary between walking downhill and uphill. Now, neither one, and this is kind of a weird argument, but this is a really good argument, mathematically, it's a really powerful argument. Does it make sense that neither walking uphill nor downhill, in the language of ants, really should be preferred over the other? I mean, they're both things that an ant can do. A function can be increasing or decreasing. Neither one should fundamentally have some greater value than the other, right? And so the boundary between the two should not get to go with one or the other concept. It's in the middle, right? An increasing function and a decreasing function are just opposite and negative slope, or positive and negative slopes, right? Does that make sense? I mean, that's kind of a sophisticated argument, but that's,
Where it has a zero slope.
say it again?
Where it has a zero slope.
Where it has, right, it has a zero slope. And you can think of it in terms of the slopes. The slopes are going from negative to positive, and zero is the boundary between the positive and negative slopes, right? So it's neither increasing nor decreasing in a valley, which we're gonna call the relative minimum, and it's neither increasing nor decreasing at a peak, which we're gonna call a relative maximum, okay? So this one would be on the interval, on that interval. Okay. Where would this function be decreasing? Everywhere else except at 4 and 7, right? It would have to have open circles there also, right? If we change this to, so that's increasing, if we kind of color code this and we say decreasing is going to be green, then that would look like that, right? Everybody agree? Okay. So in a little more formal language, this just summarizes what we just said. So there's a function. It's going to be, if b is greater than a, it's going to be increasing where f of b is greater than f of a, etc. Okay. Questions? Okay, so last issue would be then, and we're not going to spend a lot of time on this, but if we talk about a local maximum, local or relative, let's say both of those things interchangeably. So a local maximum is the same thing as a relative maximum. Local minimum is the same thing as a relative minimum. In calculus, we talk about a bunch of other kinds of maxima and minima. We talk about absolute maxima and minima. And by the way, if you collectively combine all maxima and minima combined, we call extrema. So an extremum is either a maximum or a minimum, right? It makes sense, an extreme value of the function. Okay, why do you suppose we call this local, though? But the other thing we might talk about is a global maximum or minimum. But those are for the future. For now, we're just sticking with this. But why is it relative? That's an important term. What do you think? Emma?
It's just what you see on the graph.
Kind of, but what relative or local is a good word here, right? Why do you think local is important? Because a maximum implies it's the highest.
Because it's relative to this function.
I mean, kind of. Think about the ant walking along this graph. Now, what do these arrows at the end of the graph mean? What do you think, Andrew?
It's because you measure the slope relative to those 2 points. Because you can only have a slope as long as you're comparing the position for one of those 2.
One of these. I mean, that's you guys. Those are good answers. We're kind of skirting around what I'm looking for, but it's. Yeah, different words. I'm just trying to expand your vocabulary a little bit. So now think about this ant's journey. When the ant's walking along this function, the ant can put his his flag in the dirt at the top of that function and say, I'm at a peak, right? That's something we climb mountains to get to the top and look around. Well, the ant's got a great view of the two-dimensional landscape when he gets to the top of that peak. So it's definitely a peak, right? Locally speaking, in math, when we say locally speaking, we mean in the vicinity of that point. And the language we use in math, like in calculus, we'll talk about the concept of a neighborhood in math, and that's a real word. A neighborhood means the part of the domain that's surrounding that value. So in that neighborhood of values, or locally speaking, that's the highest point. But if the ant kept hiking, could he get to a higher place somewhere? Yeah, up here, right? When the ant's up here, he's at a higher place than he was there, right? So is this an absolute, or is this a global, meaning is it the highest place on the entire two-dimensional universe this ant can walk in? No, it's not. There are other places he could go that are higher. But if he walks to the left or the right from that point, he's going down. So it is a peak, right? You get the idea? So a relative maximum is just a peak in the function, but it doesn't have to be the highest peak or the highest point. It just is a peak. So A relative minimum is just a valley. It's the lowest point in the vicinity of that point. But there might be other places that are much lower, like other, elsewhere on the graph, right? So if we wanted to come up with a really simple definition of a relative maximum, and it's a very effective one, what do you think it is? What's a relative maximum? Think about the language we've talked about today. We've just, not very much, we've talked about where a function is positive value to negative value, or where a function is increasing and decreasing. So what's a relative maximum? Describe a definition of that using our terminology from today. What do you think, Ken?
Or the positive,
Say it again.
or the positive, or the increasing and decreasing.
There you go. It's a transition from an increasing interval to a decreasing interval, isn't it? That's all it is, plain and simple. Yep.
I mean, for both of them, is where the slope equals 0.
Okay, true, it is. It's where the slope equals 0, but I could get by that. There's not enough fine print at the bottom of that contract, because I can build a function. What if this function goes up to here? And it's a good idea, but what if the function goes up to here and then it goes like that? We'll learn in calculus that there is no slope there, right? The slope, the derivative function that predicts slope doesn't exist at sharp corners, but the idea is, even if the function is not, even if the slope isn't 0, that function still works, or that definition still works. If a function is transitioning from increasing to decreasing, that has to be a peak. That has to be a maximum, right? What's going to be the definition then of a relative minimum? Where the function transitions from decreasing to increasing. That's always going to work, regardless of whether the function is smooth and we have a slope of 0 at the peak or the valley, or not. Eventually, later on in math, we'll get some harder ones where that doesn't always happen, right? But that definition always holds. Okay, get the idea? How much time we got? 6 minutes? Okay, I might as well just show you one more thing. So the other, then you guys have all day to work tomorrow. So the other thing I just wanted to kind of continue to make you aware of, and this is nothing new, is just using technology. So, okay, how would I do this? This really isn't technical. It's more of a graph one, but this is another one you're going to have. If I want to use that graph to solve where f of x equals 5, real quick, where would the answers be? This is really easy. I just want you to make sure everybody sees this. Where f of x equals 5, what am I doing? Good. So we're setting the function equal to 5, which means we want to know where is the y value equal to 5. So we just intersect the graph with a horizontal line, right? So it would be, it looks like the x coordinates are -4 and -6, right? That's different than saying evaluate, like if I were to find f of -5, well, I just want to know what's the y value when x equals -5, right? Okay, no big deal. All right, how about Okay, do you remember how to do this? Because this is the other thing I'm going to ask you to practice. If I want to find real solutions to that equation, what would I do? I'd go into Desmos, and what would I do? Okay, I could put it in. There's two things I could do. One thing I could do is I could graph the left side of the make data function, right? So I graph, y equals the left side of the equation, and then graph y equals the right side of the equation, and look for the intersections, right? The other thing I could do, if you want to, is I could put this into standard form. I could subtract 10 from both sides and get 1/2 x squared plus 2x minus 15 equals 0, and I could graph this function and look for, what? I could look for where y equals 0. Where does that happen? Oh, Chelsea. Oh. Chelsea, here's, before you go, here's something. So, what would I do? What would we do? If it said equal to 0, what would we do? What's that going to do with the graph? Where it crosses what? X-axis. Yeah, find the x-intercepts. Okay. Make sense? Well, I want to show you how to do that on a graphing calculator as well. But I'm not going to do it today. All right. We're good.